Welcome to this lesson on thermal rectifiers and phononic diodes. Today we're going to explore how nanoscale devices can control heat flow in one direction, much like electrical diodes control current. Let's start with the fundamental question. What exactly is a thermal rectifier? A thermal rectifier is a device where heat flows much more easily in one direction than in the opposite direction. It's essentially a thermal diode. Think of it like an electrical diode, but instead of controlling electron flow, we're controlling phonon flow and heat transport. Here's a visual representation. Heat flows easily from right to left, but when we try to flow heat from left to right, it's blocked or significantly reduced. This is the essence of thermal rectification. The remarkable thing is that these devices have no moving parts. They're completely solid state, relying on nanoscale engineering and quantum effects. Now you might be asking, why do we need devices that control heat flow directionally? Modern electronics, especially at the nanoscale, generate enormous amounts of heat in very small spaces. Managing this heat is critical. We need ways to protect sensitive components from overheating while allowing heat to escape in controlled directions. Beyond just cooling, thermal rectifiers could enable entirely new paradigms, like phonon-based logic circuits and thermal computing. Before we dive deeper, we need to understand phonons, because they are the primary carriers of heat in solids. Phonons are quantized lattice vibrations. When atoms in a crystal vibrate collectively, these vibrations can be treated as particle-like excitations called phonons. Here's a crystal lattice. The atoms are connected by bonds, and when one atom vibrates, it causes neighboring atoms to vibrate. This collective vibration propagates as a phonon, carrying thermal energy. In electrical insulators and semiconductors, phonons carry almost all the heat. Electrons play a minimal role. Now let's explore the first mechanism that creates thermal rectification: geometric asymmetry. Geometric asymmetry means the nanostructure is shaped differently at one end compared to the other end. Consider a tapered nanowire, wide on one end and narrow on the other. The phonon modes that can propagate depend strongly on the local cross-sectional area. When phonons travel from wide to narrow, many high-frequency modes cannot fit through the narrow region and reflect back. But when phonons travel from narrow to wide, all the modes can easily propagate and spread out into the wider region. This creates an asymmetry in thermal conductance. Heat flows more easily from narrow to wide than from wide to narrow. Here we show the asymmetry. G represents thermal conductance. In one direction G is high, in the other direction G is low. The ratio between these conductances is the rectification factor. The second mechanism involves nonlinear lattice dynamics. This is where things get really interesting at the quantum level. At sufficiently high temperatures or large displacements, the harmonic approximation breaks down. The interatomic potential becomes anharmonic. Anharmonic means the restoring force depends nonlinearly on atomic displacement. This creates frequency-dependent phonon scattering. The potential energy U of X has quadratic, cubic, and quartic terms. The cubic and quartic terms are the anharmonic contributions that create nonlinearity. These anharmonic effects make phonon properties strongly temperature-dependent. The thermal conductivity itself becomes a function of temperature gradient direction. When we apply a temperature gradient in one direction, we get a different phonon distribution than when we reverse the gradient. This asymmetry in phonon populations causes rectification. Here's a temperature gradient. Hot side at 400 Kelvin, cold side at 300 Kelvin. The phonon flux depends on the nonlinear properties of both ends. The third mechanism relies on mismatched phonon spectra across interfaces between different materials. Different materials support different ranges of phonon frequencies based on their atomic masses and bond strengths. When phonons encounter an interface between two materials, only phonons with matching frequencies on both sides can transmit efficiently. Consider an interface between material A with light atoms supporting high-frequency phonons and material B with heavy atoms supporting low-frequency phonons. The probability of phonon transmission across this interface depends on which direction the phonon is traveling. High-frequency phonons from A trying to enter B find few matching modes and reflect back. Low-frequency phonons from B can more easily find matching modes in A because A supports a broader frequency range. The acoustic mismatch model gives us alpha A, B equals 4 times ρho, A times versus A times ρho, B times versus B, divided by the quantity ρho, A times versus A, plus ρho, B times versus B squared. Here, ρ is density and V is sound velocity. By engineering interfaces with strongly mismatched phonon spectra, we achieve significant thermal rectification. Now let's discuss how these principles are implemented in real nanostructures, starting with nanowires. Researchers have fabricated silicon nanowires with controlled diameter variations along their length. A typical design varies from 50 nanometers diameter down to 20 nanometers. The geometric asymmetry creates preferential heat flow. Carbon nanotubes can be functionalized with different molecular groups on each end, creating mass asymmetry. These nanowire rectifiers typically achieve rectification factors between 1.2 and 1.5, meaning heat flows 20 to 50% more easily in one direction. Another approach uses multilayer structures with alternating materials. A multilayer structure alternates between materials with very different phonon properties, such as graphene and silicon. Each interface acts as a frequency-selective filter. The cumulative effect of multiple interfaces enhances rectification. Using graded interfaces where composition changes gradually rather than abruptly can improve phonon transmission in the forward direction while maintaining blocking in reverse. The most sophisticated approach uses phononic crystals, which are periodic nanostructures designed to manipulate phonon propagation. Just as photonic crystals create band gaps for light, phononic crystals create band gaps for phonons at specific frequencies. A phononic crystal consists of a periodic array of inclusions in a matrix material. The periodicity creates forbidden frequency bands. By designing asymmetric unit cells, where the scattering centers are not symmetric, we can create directional phonon transport. We can engineer the phononic band structure to allow certain frequencies in one direction but not the other. The dispersion relation omega of k vector does not equal omega of negative k vector. This non-reciprocity in the band structure is key to rectification. A critical question arises: how large must the temperature difference be for thermal rectification to be observable? Most thermal rectifiers require temperature differences of at least 50 to 100 Kelvin to show measurable rectification. The nonlinear effects that drive rectification become stronger at higher temperatures where anharmonicity dominates. A typical operating condition might have a hot side at 500 Kelvin and cold side at 300 Kelvin, giving a 200 Kelvin temperature difference. Let's explore the first major application, on-chip thermal management for integrated circuits. Modern high-performance processors generate power densities exceeding 100 watts per square centimeter. This creates severe thermal management challenges. Local hotspots can reach temperatures that permanently damage transistors or degrade performance. Here's a chip layout. The CPU core generates the most heat. We want heat to flow downward to the heatsink, but prevent heat from flowing laterally into sensitive memory or cache regions. Thermal rectifiers placed strategically can direct heat preferentially toward heatsinks, while blocking lateral heat spread. This protects temperature-sensitive components like SRAM cache and analog circuits from thermal interference. The second application is phonon-based logic, a completely new computing paradigm. Instead of encoding information in electron charge or voltage, we encode it in phonon pulses, packets of thermal energy. Thermal rectifiers can act like transistors, controlling whether phonon signals propagate or are blocked. A phonon logic gate uses thermal rectifiers to control signal propagation. Input phonons can be gated by controlling the rectifier properties. Phonon-based computing could potentially operate at much lower power than electronic computing, because phonons don't suffer from Joule heating. However, challenges remain in achieving high-speed operation and integrating phonon logic with conventional electronics. The third application is thermal protection of sensitive components by enforcing one-way heat flow. In quantum computing and sensitive detectors operating at cryogenic temperatures, we need to prevent heat from flowing into the cold region. At the same time, any heat generated by the cold components themselves needs to be able to escape to the heatsink. The thermal diode allows heat to flow out from the quantum processor at 4 Kelvin to the heatsink at 300 Kelvin, but blocks thermal radiation from flowing back in. This dramatically reduces thermal noise in sensitive quantum measurements and extends coherence times. What kind of performance have researchers actually achieved with thermal rectifiers? Most experimental demonstrations report rectification ratios between 1.2 and 2.0, meaning forward conductance is 20% to 100% higher than reverse. The rectification ratio R equals G forward divided by G reverse, where G is thermal conductance. The best reported results achieve rectification ratios up to 3.0 in specially engineered graphene silicon multilayers. These devices typically operate in the temperature range from 100 Kelvin to 600 Kelvin, where nonlinear effects are significant but materials remain stable. Here's typical data showing rectification ratio R versus temperature. R increases with temperature as nonlinear effects become stronger. What are the theoretical limits? How much rectification is actually possible? Interestingly, the Carnot efficiency limit that governs heat engines does not directly apply to thermal rectifiers because they're passive devices. The maximum achievable rectification ratio depends fundamentally on the nonlinearity of the materials and the degree of structural asymmetry. Theory predicts R max is approximately exponential of delta T divided by T average, where delta T is the temperature difference and T average is the average temperature. The major challenge is fabrication. Creating these asymmetric nanostructures with the required precision is extremely difficult. Another challenge is material stability. Many materials that show good rectification degrade or interdiffuse at the high temperatures needed for operation. What does the future hold for thermal rectifiers and phononic devices? Two-dimensional materials like graphene, molybdenum disulfide, and phosphorine offer new possibilities due to their extreme thinness and tunable properties. Researchers are using machine learning to optimize the complex geometries and material combinations needed for maximum rectification. A key goal is integrating thermal rectifiers with existing CMOS semiconductor manufacturing processes. The future applications span Phonon-based logic for computing, advanced thermal management for high-power devices, and protection for quantum systems. You might ask, why can't we just use mechanical valves or moving parts to control heat flow? At the nanoscale, there's simply no room for mechanical components. We're talking about devices only tens of nanometers in size. Moving parts add enormous complexity, require actuation mechanisms, and introduce failure modes. Solid-state thermal rectifiers with no moving parts are inherently more reliable and can be mass-produced using standard lithography. It's instructive to compare thermal rectifiers with their electrical counterparts, the p-n junction diodes. Electrical diodes achieve forward to reverse current ratios of 1,000 or more, vastly better than thermal rectifiers. Thermal rectifiers currently achieve ratios of only 2 to 3. Why the huge difference? The fundamental reason is that electrons are charged particles that respond to electric fields, allowing strong control. Phonons are neutral quasi-particles with no charge. We can only control phonons through structural modifications to the material itself, which provides much weaker control than applying a voltage. Here's a comparison. Electrical diodes with rectification ratios of 1,000 versus thermal diodes with ratios around 2. Both are useful, but operate on completely different principles. To fully understand thermal rectifiers, we need to consider different phonon transport regimes. In the ballistic regime, the phonon mean free path is larger than the device size. Phonons travel without scattering. In the diffusive regime, the mean free path is much smaller than the device. Phonons undergo many scattering events. The thermal conductivity lambda equals V times tau divided by 3, where V is phonon velocity and tau is scattering time. This is the kinetic theory result. Thermal rectification can occur in both ballistic and diffusive regimes, but the microscopic mechanisms differ. In the ballistic regime, rectification comes primarily from geometric mode filtering at boundaries. In the diffusive regime, rectification arises from nonlinear temperature-dependent scattering processes. An exciting frontier is phonon hydrodynamics, where phonons behave collectively like a fluid. At intermediate temperatures and very pure crystals, phonon collisions dominate over other scattering mechanisms. When phonons scatter primarily with each other, they can flow collectively like a viscous fluid, exhibiting phenomena like second sound. The phonon viscosity eta equals C times versus squared times tau divided by 5, where C is heat capacity. In this hydrodynamic regime, thermal rectification could potentially arise from fluid dynamic effects like vortices and turbulence. How do researchers actually measure thermal rectification at the nanoscale? The 3-omega method uses an oscillating current through a thin wire to measure thermal conductivity with high precision. Time-domain thermoreflectance uses ultrafast laser pulses to measure thermal transport on picosecond timescales and nanometer length scales. Scanning thermal microscopy uses a sharp probe to map temperature with nanometer resolution. A scanning thermal microscope raises a sharp heated probe over the sample surface, measuring local temperature and thermal conductance at each point. Theoretical understanding relies heavily on molecular dynamics simulations. Molecular dynamics simulations track the motion of millions of atoms as they interact through interatomic potentials. From these trajectories, we can calculate phonon dispersion relations, scattering rates, and thermal conductivity. The force on atom I equals negative gradient of I of the potential energy U, which depends on all atomic positions. These simulations enable us to test theoretical predictions about thermal rectification mechanisms before fabricating devices. The main challenge is computational cost. Simulating realistic devices with billions of atoms for long enough times to observe thermal transport remains extremely demanding. Let me summarize the key concepts we've covered about thermal rectifiers and phononic diodes. Thermal rectifiers are solid-state devices that enable directional heat flow, analogous to electrical diodes. The three main mechanisms are geometric asymmetry, nonlinear lattice dynamics, and interface phonon spectrum mismatch. These principles are implemented in nanowires, multilayer structures, and phononic crystals. Applications include on-chip thermal management, phonon-based logic, and thermal protection of quantum devices. Current devices achieve rectification ratios between 1.2 and 3.0, with ongoing research pushing toward higher values. What are the remaining open questions in this field? Can we design structures that achieve rectification ratios above 10, approaching the performance of electrical diodes? Can we create thermal rectifiers that work efficiently at room temperature with small temperature differences? How do we integrate thermal rectifiers with conventional CMOS electronics manufacturing? The ultimate question, can we create thermal transistors with gain, where a small thermal input controls a larger thermal output? Thermal rectifiers and phononic diodes represent a fascinating intersection of nanotechnology, quantum mechanics, and thermal physics. This field bridges fundamental science about how phonons behave at the nanoscale with practical applications in thermal management and computing. As we gain better control over phonon transport, we're enabling entirely new paradigms in thermal engineering, where heat flow can be precisely controlled and manipulated. The future of thermal management is directional, where we can route heat like we route electrical signals in circuits, opening up possibilities we're only beginning to imagine.